Here in the big data architectures track, we'll look now, and that's quite interesting, on how to build a modern analytics processing pipeline. CDAs, cross-device analytics, provide person-centric reporting capabilities in Adobe Analytics, reports by grouping devices belonging to certain identities. We will look at what was their innovative setup in 2016 when they started working on this solution and what persuaded them to migrate towards Databricks and Delta, making it capable of handling billions of events per day. Really looking forward to that. Let's hear the story of this journey from Andrei Smarandoiu, software developer engineer, and Razvan Burlacioiu, senior software engineer and team leader at Adobe. Two technical professionals who fostered their passion for big data technologies by tackling interesting problems while working on data processing pipelines. Andrei, Razvan, thanks for being here, and let's give it up for those guys.
Thank you, Danny. Thank you for the kind intro. Hello, everyone. Very thrilled to be here. I'm Razvan Burlacioiu. I joined Adobe in 2016, so almost 6 years ago. Next to me is Andrei. He joined us in 2019, I think, so 3 years ago. Anyway, you can tell that I'm slightly more experienced than him in maneuvering the big data because I'm, more bigger. Anyway, thanks for joining our session. Today we're gonna talk about our journey, which started in 2016, as I mentioned. So our main focus during our tenure at Adobe was mainly to work on a sub-product of Adobe Analytics, and technically speaking, a secondary processing pipeline in which we will deep dive too. I'm proud to say that this product started, as I mentioned, in 2016 and launched in 2019, and it was 100% made here in Romania. And yeah, I guess that's pretty awesome. Cool. So today we're gonna walk you through a set of milestones and challenges that we've encountered. We hope that you'll find those insightful and maybe consider them with a grain of salt, of course. Good practices that you might apply also for your data processing pipelines. And we'll also deep dive in the solutions, as I mentioned. But first, to set up the context a little bit, so Adobe Analytics is one of the Experience Cloud's flagship products, among others. It's been quite a while since its launch. I think it's all in its entire existence, it has almost like 20 years or so of crunching big data. It enables digital enterprises from all over the world, from various industries, to gain insights from their data points, which can be pretty much anything for a matter. So when you have applications in banking, finance, retail, a lot, hospitality, transportation, you name it. It's there. So what Adobe Analytics empowers users to do, analysts mostly, is to do segmentations, flowcharts, Venn diagrams, all of those attribution, all of those cool things in a matter of seconds, and that's actually a big deal. So you can get pretty quick insights without having to crunch a lot of data on your own stack. All in the hopes of building better customer experiences, of course. Cool. So even though Adobe Analytics is quite broad in tooling and features, there's still some use case which requires further attention and cracking, which can't be solved without the feature that we're working at. So I'm going to showcase here a journey, which nowadays I think is pretty common. So most of us have more than one device, right? So we have like a personal tablet, personal phone, smartwatch. I know we're cross-devicing everything. Our experiences are cross devices. So the challenge usually is that we don't have a unified vision of this journey, right? So let's say we have the following experience. So we're interested in buying a new pair of shoes. We start searching in our favorite search engine, I don't know, new shoes, then actually see a retailer's website. We would check that, and that's about it. We get distracted with, and that activity. So later on, when maybe we're commuting, oh, I remember I need to buy shoes. Okay, so I load my native app. I actually view a shoe that I like, a pair of shoes. I actually share that on a social feed with someone, get their approval, yay. Okay, and commute ends, then I go home, I eat, and I follow up on my personal PC. I actually want to buy these shoes. I configure the size, the color, and so on. I check out and I buy the pair of shoes. So that's pretty much it. And later, the next day, probably I'll go to work and wonder where are my shoes? Will they be delivered today? What's the status of my order, basically? So you can see that this flow is pretty complicated. It's composed out of 4 individual devices, which have 7 distinct actions. But is that meaningful to an analyst which is trying to make sense? What drove the conversion? To whom I can attribute the purchase, right? And it's pretty difficult because with the device-centric reporting capability, you would only see 4 visits, which are the verticals described over here, right? So you would see a laptop which started buying shoes but never purchased them. Someone who's viewing on a native app a shoe and sharing it. And someone who actually buys the shoes, and that's about it. So this is not meaningful. So what we do is that we connect the horizontal lines for the analysts, transforming a device-centric reporting capability into an identity-centric capability, or more usually a person-centric capability. Cool. All in the effort to understand the better interaction with the brand. Simply put, grouping a bunch of data and mapping at high velocity and stuff like that with this cheesy ribbon. Cool. So a few cross-device analytics in numbers, a few stats. We crunch about 4 billion events per day. In Super Saiyan mode, we can also do 20 during some days of the week. We have multi-region deployment, of course, in the main sites. We have about 100 customers above that, actually. The team is composed out of 6 unified engineers. I'm going to dip into that. But before, I'm going to give credit to our product manager, our engineering manager as well, and the customer success engineer. So their help is invaluable in our work. But I just wanted to showcase here how many people it takes to operate like day-to-day work, on-call stuff. So this core team basically develops, tests, operates, monitors, and does on-call on the stack that we are about to showcase. Cool. And another cool stat, it took us around 50K plus since 2016 of effort to reach this point. Some other random stats, I don't know, 500 nodes, something like that, thousands of cores, terabytes of memory, and you can meet the entire team actually here. They're in the front row. Hey guys, I'm just embarrassing you. Cool. So we're going to start with a very high-level, oversimplified, high-level diagram of our architecture. So I guess we can pretty much break down any processing pipeline, any processing analytics, solution into 3 main pieces. We have the collection layer, the processing layer, and the reporting. Now, the challenge at hand in 2016 was not only from a functional perspective, the bar was pretty high because Adobe Analytics, the core product, the main processing pipeline was already processing billions of hits per day. So we had to address that, and we actually started onboarding large customers from day one of the GA. So here will be exemplified only the smaller pieces, which are, I guess, are takeaways for other architectures. At the moment, we had Kafka integration, which would stream a click stream of events, right? We would have an ingestion layer. For our business processing use case, we would have this short-term store here, from which we would serve as a source for batch processing. And here we would have various chain streaming apps. This is again oversimplified, refining the data more and more until it landed in a data lake, right? Among the lines, we would see various REST APIs which are relevant for business processing. And it's also interesting the part with the long-term store, where we would have data archived into the long-term store and then listened all over again for months or even years, right? So to give some additional detail to this, we actually have Spark streaming applications. So those are like self-contained Spark clusters, which are independently running, refining the data more and more. They have an at least once processing guarantee semantic here, back pressure, and Andrei will deep dive in the challenges that we've encountered along the way with this. We started with HBase here, and for the long-term store we had a plain HDFS at the moment. Cool. So a few words about our vision and about infrastructure. So again, we started in 2016. We wanted to run large-scale applications. We actually emphasized on being cloud agnostic. So we wanted to kind of be easy to lift and shift data from a cloud provider to another. So and just rent the VMs from them. We wanted to, we already have solutions which had large established deployments of Cassandra and HBase, and maybe you attended Sherban and Stefan's talk yesterday. So the technological advancements at the moment enabled us to do it kind of further. So we basically containerized those big data monsters and have them run for us in a packed environment. Cool. In the interest of using every bit of resource of CPU and memory, have those daemons isolated instead of having maybe like one VM per daemon, because I'm scared that my Zookeper will be killed if I put a data node next to it. I don't know, something like that. The functional specs of the production environments are the same as in the other environments, so we don't want any surprises to that. And we wanted a self-service way. So as an engineer who is starting some R&D work, and I want to enable the full power of the team to be self-service and not hit a ticket, a wall of tickets somewhere and waiting for them to be resolved. So in that sense, the philosophy that we applied was that basically any infrastructure that we would use would be created first in the cloud, then we would provision it, do some sort of namespacing so we can collocate 7 dev environments in one cluster, 2 QE environments and so on, and even do that in prod with multiple tracks of processing. And ultimately, we would do component deployment, and not only applications, but alerts, dashboards, so everything would be treated as an artifact, and I would be able to tear down and construct worlds on a daily, weekly basis, enabling us to be efficient in development. Cool. So a fun image of our architecture, or how it looked like. We started with Mesos. There was there was Kubernetes, but it was not like ready for big data application at the moment, I guess. FluentD for log forwarding, HBase, as I mentioned, our choice for a key value in memory store. Apache Zeppelin, Andrei will dive into that. Kafka, Spark, Prometheus, Grafana, MongoDB. So this was the initial stack. It was interesting and pretty packed, and you could spin all those infrastructure right away. Cool. So going back to the system. So as we reached the maturity and we were preparing for GA, we kind of ended this POC mode of things. So we started externalizing some systems, right? So we don't operate Kafka, for example, anymore. That's the core services team's job. Or we didn't store the long-term storage in our own HDFS. We would use an HDFS compatible interface, S3, Azure Data Lake, something like that, offload it into the cloud. But we got stuck with HBase because we required at the moment low latency lookups initially. Cool. So on that note, I'll hand over this to Andrei. Have fun.
Yeah, thank you, Razvan. It's so good to be here. We look at a series of challenges that we faced and ways that we've managed to solve them. One of them is how we've designed and implemented the functional testing. So we've implemented unit tests to test blocks of code in isolation and for both successful and erroneous scenarios. We've implemented service level testing to test the unit services. with mocked data. Both these types of tests we've included at build time in order to make sure that each release covers the functional requirements. And we extended the scope, and we've designed this integration testing framework that we are using to test applications in isolation. So this framework will publish bronze events, silver events, and golden events to the input of each application, mainly through Kafka topics. So what are these events, you may ask? We've seen in a previous presentation. So basically, the bronze events are data received at collection time or raw data. Silver events are data post-processing, and golden events are aggregated data or data with business value. So these applications will process this data and write that to a Kafka topic or an HBase table, from where the integration testing framework will come and compare those results with the ones that were written, basically finishing the cycle of the integration test. But what about the non-functional testing? Well, for that we've implemented a synthetic traffic generator that writes the same types of data as mentioned before, the bronze, silver, and golden events, to one of those two sinks, the HTTP sink or a Kafka sink. So we are using this to test the end-to-end functionality of the changes that we've implemented on one application, or for the reliability and the performance of that application. So basically, this is the last step before promoting these changes to the stage environment, where we test with real traffic from our synthetic traffic clients. Yeah, so we understood that in the future we will onboard the real customers, so we needed to be prepared to perform extensive validation and exploratory analysis. So for that, we've implemented Scala notebooks to perform ad hoc data investigations. Initially, those were run and stored in Apache Zeppelin, but were later ported to Databricks. Then we've implemented an analyzer tool to evaluate the data in different stages of our processing pipeline. This tool generates daily quantitative and qualitative reports that are sent via email that we can analyze during on-call. And on top of that, we've implemented our in-house exporter written in Scala that basically evaluates the same types of data, but instead of sending via email, it generates metrics that are later scrapped, but that are exposed in Prometheus format and scrapped by the Prometheus server, which further down the line transforms in alerts and dashboards. Okay. So we reached the year 2019. It was a bad year because COVID happened, but some good things happened, and those are, we started the preparations to become GA. So we set up our multi-region production environment. We onboarded our synthetic traffic clients for end-to-end validation. We defined the runbooks and operation documentation that we held in GitHub for versioning purposes. We set up our dashboards and alerts that we made sure that cover all functional domain. We set up disaster recovery clusters and backup and restore jobs. And ultimately, we set up the on-call procedures and starting doing on-call by integrating with PagerDuty. So the moment came and we onboarded our first real customer and the fun began. But it's not the kind of fun that you'd expect. We faced a new challenge. And as we onboarded more and more clients in time, we noticed that our applications need to be deployed on specialized VMs, and that can be memory intensive, CPU intensive, storage intensive, and so on. Not only that, we noticed that the clients onboarded in different regions have different needs, and their data looks also different. So on one region, we can have clients with a higher throughput, more data stored. Or in other region, we can have more data privacy requests. So we need to be versatile across regions as well. And we also noticed that our Spark deployments, or the containers of our Spark deployments, could collocate on the same VMs as the HDFS pods. These VMs are general purpose by design, so they were pretty expensive. So in order to tackle all these issues, we made use of the virtual machine scale sets and defined these types of instance families, CPU intensive, memory intensive, and storage intensive VMs. And as an implementation, we made use of the Mesos' placement constraint feature, or affinity and anti-affinity rules constraints, to be able to orchestrate these containers and pods to land on these types of VMs. Therefore, we were able to alleviate the noisy neighbors effect, and in the process, we also reduced the COGS model significantly, I'd say. Okay, so a new challenge. This one happened in the multiple applications, but for the sake of exemplification and time, I will concentrate mainly on one, the data privacy processor. So initially, when you had few clients, this was a trivial issue because, as I said, we had few clients and even fewer of them were sending data privacy requests. But in time, as we onboarded more and more clients and more of them started sending data privacy, and the data accumulated in our store started to grow, we started seeing this issue. We can see here an example of how this process of obfuscating the data looks like in the data privacy executor. So we can see that. So firstly, here we can see tasks running on different executors. One task is basically loading one partition from our store, obfuscating that data or anonymizing that data and writing it back in the store. So you can see that on core 2, it basically got a higher partition, so it will take more time to process than on the other executors. But not only that, we noticed that the other executors will also be idle during the process of core 2 in executor 1. So there is a lot of idle time for these cores. One thing that I forgot to mention is that here is the representation of only one batch process in Spark. So the reason the other cores are idle is because this batch needs to finish before starting a new one. So by knowing this, we understand basically the solution to optimize this process, which is basically to merge multiple Spark batches, and process them all together, so that when the tasks are generated, when the other cores finish, they have other partitions to access in order to speed up the process. So this effect can be seen in this second diagram. After testing this feature, we've noticed significant improvement in processing of up to 3x, and we were also able to scale the application even better. Okay, another challenge. So joining a clickstream of events can be sometimes challenging. We need to make sure that we have a flow control and we implement some back pressure mechanisms, or we make sure that their handling is done right. We have at least once processing guarantee, that we can adapt to unusual flow patterns, or in this case, to make sure that if we have an integration with an external service, that we maximize the throughput of our QPS. Here is an example that we've noticed in our Spark, our streaming processor. So we noticed in production that our streaming processor application was not scaling anymore. So because it reached this global QPS agreed with the vendor pretty easily, I'd say. So this was an issue because we couldn't scale the application anymore. So here is an exemplification of that issue. Let's say that we've already read the data from Kafka, and the hits have an additional attribute of color to better exemplify this. And we look only on one partition, one Spark partition. So after grouping this by color, we notice that we obtain 4 batches. And for each one of these batches, we'll send a request to the REST API, resulting in only 4 QPS made to the identity service. So that's the external service. But this is a trivial issue for one partition. But when extending to 2 partitions, again, for exemplification purposes, the second partition will have the same hits, and will generate the same number of requests, meaning that we'll ultimately make 4 requests instead of 8 requests instead of 4. Sorry. This is because as you can see, for each color, we send 2 requests, and intuitively we can understand that we can group actually this together and obtain only 4 requests. So how can we achieve that? Well, we used Spark's range partitioner to obtain that. So before grouping this by color, we can rearrange the data, repartition the data by a key, which is, in this case, is the color. And we could obtain the partitions like this. So we can see that instead of sending 8 requests, as in the previous example, we now send 5. But why 5? We should have obtained 4 as ideally, let's say. Well, the Spark range partitioner has a limit per partition of hits that will send to 1 partition. In this case, in case of color gray, it only sent 1, and the partition 1 was full. So it continued on the next partition, but it's still a great decrease in the QPS. So let's see the results. After implementing this in the streaming processor, we can see in this diagram that the number of requests per second made by the application, and there when we see that drop, the sudden drop, that moment represents the actual rollout in production of these changes. So we can see that from 50-60 requests per second, we dropped all the way to 5 requests per second. All of that with the same number of resources. And we also gained the ability to scale this application even further, which is actually the main point. Okay, another challenge. Once again, we come back to onboarding more and more clients, which for us is a big issue because we are a multi-tenant processing pipeline. So the clients have different data. Some can send the data with a higher payload. Some can send the higher throughput. Some can send data that have many device transitions. Some can send data that accesses too many partitions, or a combination of these. So we need to be armed with the possibility to segregate this traffic in multiple applications, a process which we call bulk heading. We can segregate the traffic by aspects such as frequency, volume, or the nature of the client's data. By using this, we can isolate clients that have an unusual traffic pattern, and also we can optimize each application based on the traffic and nature of the client's data that reside on that application. And challenge 8, moving on. We come back to the data privacy processor for this one, which does data restatements across a wide span of partitions. So the way we chose the partition keys in our data lake was designed to not generate too many partitions in order to avoid the small files effect, which would decrease the write capabilities, and also not generate too few partitions in order to make use of the effects of partitioning at read time and not decrease that as well. So we have a balance here. In this case, to exemplify what data privacy means, we receive a set of rows for to be anonymized. Each row corresponds to one partition in our data lake. So in order to anonymize one row, we need to load that partition from data lake, anonymize this row in memory, and override the entire partition back in the data lake. So basically, to anonymize millions of hits, we need to actually process billions, which is a huge deal because it generates huge write amplification effects. So to see how we actually tackle this, I'll invite back Razvan to show you.
Thanks, Andrei. Cool. So yeah, this one was harder to crack. Actually, it was the moment when we had to take a step back and look at the overall architecture, and also take into account recent advancements in data processing pipelines in terms of technologies. So TLDR is that we have the left-hand side of the processing layer, which is kind of in the Hadoop era, right? downfalling. This is more modern with data lakes, but each of these have pros and cons and pitfalls. We actually took a step back, as I mentioned, and reassess our product requirements from end to end. And it turned out that although we love this stack, we didn't have too much problems with it. We didn't require like real-time processing, at least for our processing pipeline. There are other pipelines for real-time processing in that sense. So because now here we do fast processing, 20, 60 seconds, micro batches, and here we do like 5 minutes, 15 minutes micro batches. So I guess the latency is as good as its weakest link, which is here. So we kind of wanted to even the balance, right? To make this faster and this slower because it's okay. We found out that that's doable. Cool. So we took a step back, as I mentioned, and started acknowledging what are the pros and cons of each stack, because they have both pros and cons. So we like HBase because it's usually cheap to do individual lookups and data restatements, mutations. You just ship them, and there's minor compactions that happen and clean up the data. There's consolidation in that sense. You have dynamic partitioning. Yeah, so that's cool. But the not so fun part is maintenance. Yeah, you have to do it on your own. There were some cases where we had to exercise our business continuity and disaster recovery plan because the cloud provider basically erased 5 VMs under our HDFS within 10 minutes. So it was close to re-replication, but that didn't happen. So we had to initiate the restore backup, and everything went well, but it was quite an effort. It's more expensive, I would say. We keep replication factor of 3 here. We find that that's a good trade-off. But I would say that in this situation, it's usually costly per terabyte to operate HBase. And because we love Spark, we would use the HBase client from Spark and not actually gain all that value that Spark does with the query planner and push down predicates and stuff like that. We would bottleneck and have to here at Spark ends, and from here on we need to tune the HBase client. And by the way, we did that several times to achieve performance. Cool. On the right hand side, sorry. What we do like about HDFS cloud interfaces like S3, like Azure Data Lake Gen 1, Gen 2, anyway, and so on, is that the fact that they're managed, right? So you don't have to do anything. It's nice. I mean, you can set stuff like replication, hot tiers, hot, cold, stuff like that, but that's pretty much about it. I would say it's cheaper to store in terms of the terabytes, cost per terabytes in storage and transactions. The pitfall is what Andrei showcased earlier, is that in order to do an individual data restatement, you'd have to load the entire immutable file, do an anti-join in memory, whatever you want that means for you, and then restate the data. But this has the advantage of being Spark native, so you would have Query Planner be involved in all the steps of the processing. And unfortunately, there's no out-of-the-box consolidation. So I really like in HBase that you have dynamic partitioning, you have minor compactions. Those things are fast, but not here. You would have to do this on your own. If I have, I don't know, a spike of traffic and there are 5 batches which are big, those will create problems upon read. So I would need to have like this other job which would do compaction on my behalf to speed up the data upon read. So we took these notes and started looking at what's out there in the field. So we know our attention went into table formats. Yeah, so this was like 2020, around 2020, and we started actually transitioning towards this. So we were in a odd situation. So we were container native from 2016, but our Arc was not Kubernetes. So, and Kubernetes didn't provide a straight out of the box solution for a lift and shift operation, right? So you don't, today you have some HDFS deployment in Kubernetes, but nothing which are mature enough, I would say. You don't have operators for HDFS and so on. Cassandra has a better faith in that sense. But I guess HDFS just didn't cross the chasm of Kubernetes nativeness, not cloud nativeness. And yeah, that was pretty much about it. We couldn't just lift and shift Kubernetes, so we had to take a step back and reassess what's our use case, what are requirements, and see what other technologies are there. So yeah, generically speaking, table formats are a storage abstraction layer. So it's a data lake on steroids, I would say. If I go back actually to the high-level diagram that I showcased here, sorry. Here. You would notice immediately that in the data lake layer, you would have a data path, which is the data lake event streamer and the data lake event listener. So this is a very data-intensive path. And then you would have an external service, which is separate, can be a REST API, can be a database of some sort anyway, which knows where to do lookups, right? So it's like a catalog of searching for things. Where's my data in the data lake? Like a secondary index of some sort. So this architecture has some challenges, of course. You need to have good error handling, race conditions. Data has been written here. This was not completed. Anyway, a lot of boilerplate that needs to be done here. You need a batch, write it, then complete it, then notify the interested parties, so on. So this doesn't scale good enough, I would say. So table formats, I've named a few. The most popular ones are Delta, from Databricks, Iceberg, Apache Iceberg, and Hoodie, which actually stands for Hadoop Update Delete Inserts. Anyway, it brings new semantics to the data lake that you wouldn't have out of the box, as I mentioned here. So instead of having an external service for your data lake to manage, you have an secondary index with the data itself. So all your big data applications like a Spark would have the ability to crunch that index first and only access the data if it needs to. I'll give you an example. So when we started piloting this, we did a count on 11 billion events. It took 8 minutes with a $3,000 infrastructure per month cost. So it took a few minutes to basically unpack all those Parquet files, count them, and so on. With a table format, it took a few seconds, because to do a count, you just need to search the index, sum it up, and that's pretty much it. You don't have to actually see the payload for this operation. But of course, this doesn't solve all the pitfalls of data lakes, but it makes it alleviates them. So we have scalable metadata handling index, a lot of data skipping techniques. So the table format knows exactly where not to look when you're searching for stuff. Runs on chip storage, as I mentioned, we like that. No operational maintenance required. Has built-in tooling for data governance, and you would say that's not much, but it is actually. So you can do apply retention using a Spark SQL query. That's it. You don't have to go and delete data by yourself. You have those optimizations that I was talking about in HBase. So you have the idea of running an optimize, and this will trigger a Spark job which bin packs data, does compactions on your behalf, yeah, and also has a vacuum feature which basically cleans up orphaned data, which is pretty much the similar way that HBase does. You also get all these cool features. So row level upsert, this is the main focus point. Schema evolution, snapshot isolation, so you can do select, blah, where, as of timestamp, so you don't have to know where to search for the data. Transaction change logs, point in time restores or disaster recovery would look like, hey, restore my table state like 3 hours ago, and just I don't have to do a backup restore because versions of the data will be kept for some time there. There's some support in multiple writers, so you'd have two writers competing for the same partition. At least it won't allow you to corrupt the data lake. It will blow up in your face. And it has built-in consolidations features, as I mentioned. So we're going back to our initial architecture. So how does this look like today? So there are some changes and further others more to be made. We basically replaced the short-term store, which contains terabytes of data, with a Delta table, right? When we have the same component, Delta Lake Event Streamer over here. And we would also adapt the long-term store, the golden table, to write in that table format. So we don't need this anymore, because it also table formats, at least some of them, provide some features such as change feeds. Yeah, so you can subscribe to that change feed, and you would say, hey, I added this, I deleted that, I updated that, and so on. And you can do incremental processing based on it. Cool. So instead of a conclusion, because yeah, there are a lot of things to say. Our journey was definitely exciting, not boring, and far from over, I bet. We continue to push the limits on our processing pipeline. We still onboard a lot of customers, and they have various data patterns that surprise us every now and then. The technological landscape, of course, changes every day, and I would say that table formats are a good focal point, at least for some use cases. I mean, take this with a grain of salt. Understand your requirements and maybe consider them. Maybe not for like real time, but it's more like a good choice for optimizing throughput rather than latency. Yeah. Cool. Thank you so much, all of you, for your attention.
Thank you, gentlemen, for your consistent contribution. If we have questions, please, yeah.
Hello, thank you for your presentation. So we tried using Hoodie about 3 years ago for this similar use case for GDPR and right to be forgotten, but performance was terrible. I mean, we ended up just reading the Parquet files, filtering and writing back. What's your experience? Did you use Hoodie or did you use something for Databricks? When was that? And I don't know, is it worth trying again?
I would say from experience, we tried Hoodie because it was out of the box and open source in a Garage Week project. We spent like 1 week trying to understand those semantics, but we ended up using Delta because we have a partnership with Databricks. So, by the way, the Spark workloads are now migrated into Databricks. We don't have that old stack anymore. We didn't feel the need to lift and shift Spark in Kubernetes, at least not at the moment. So due to our partnership with Databricks, we have this and also access to table formats and Delta. And I would say, yes, probably it depends on the use case, but that superset of features that I showcased, not all the table formats have them. For example, at the moment, Iceberg doesn't have row-level upserts, but there's an open issue to that, and it might have someday. So I guess it boils down to understanding your requirement and understand each of these options and pilot the one that you best see fit. I'm afraid I don't have a straight answer on that. Sorry.
Any other questions? Or question, I might say. Thus being said, gentlemen, we kindly thank you.
Thank you.